Okay, for today's pre-lecture video, we're going to take a closer look at the idea of energy when we're talking about gravity. Remember that in this chapter, we're talking about gravity for things like planets orbiting the sun or satellites orbiting the Earth. And so the form of gravity has a different form than what we were used to when we were dealing with locations close to the surface of the Earth. So if we're talking about satellites, we just want to remember the terms or how we wrote the potential energy. So the potential energy of an object, like a satellite orbiting the Earth, was found to be minus big G, the mass of the satellite, times the mass of the Earth over the radius, where this would be the distance from the center of the Earth. Now, we're actually going to start at the surface, so we don't have a distance closer, and that would be when the distance is the radius of the Earth, and then as it goes up towards, higher and higher distances. Some things we notice about the potential energy is that it's negative, and that might be uncomfortable, but that's okay. That is something that we want to remember for next semester, because it actually represents the fact that the force that it is associated with is an attractive force. And so that negative sign actually means something. In the end, we can sort of see that if we look at the change in potential energy as we go from one location to the other, because it'll represent the work that gravity would have to do. And then we could see that, because if we're separating the objects, that's going to take a positive amount of work because it's an attractive force. So don't get too worried about the fact that the potential energy is negative, and just remember that it has something to do with the force that it's associated with. In this case, it's the force of gravity. And then, of course, we also have the kinetic energy of the satellite, which would be 1/2 the mass of the satellite times its velocity squared. When we're dealing with energy, we would say that, of course, the total energy is going to be the potential plus the kinetic. And we will usually deal with situations where that energy is going to be conserved, and so that would remain a constant term. Put together, it would look something like this. The total energy. Now, a special case is if we have circular orbits. If we have a circular orbit, so here we have the Earth, and then we have a satellite that's orbiting, and let's pretend it's a circular orbit, the distance of r. We could say that the force of gravity is going to act as a centripetal force. So when we do Newton's second law, F equals ma, we'd put in the force of gravity, and then that's equal to the mass of the satellite times its acceleration. And we can actually use this to sort of modify the expression for the energy of the satellite. Again, remember that we're doing it just for circular orbits. So just to remind ourselves, the energy for the satellite is minus the mass of the satellite times the mass of the Earth over r, and then plus the kinetic energy. So the first term, of course, was the potential energy. The second term is the kinetic energy. And what we're going to do is we're going to actually solve for the velocity squared and then use that in this expression for energy. So let's rearrange a little bit. First, we can get rid of the mass of the satellite. That doesn't actually matter. So we get G times the mass of the Earth over r is equal to v squared. And so we're going to put this in the energy term. And notice that when we rewrite that velocity term and replace it into the kinetic energy, so we used the fact that it was a circular orbit, the term for kinetic energy ends up looking a lot like the term for potential energy. And those can be easily added together, and we get minus g m, mass of the satellite, mass of the Earth, all over 2r. It's still negative, and that represents something. In physics, the fact that the total energy is negative actually refers to the fact that in these cases, the orbits are bound. And what that means is that, the total energy of a satellite that is in a bound orbit with the Earth is always going to be negative. You might think back to the energy of an electron in an atom and remember that those energy levels for the electron were actually negative values. And when it got up to 0, that was the point where the electron could escape. And the same thing is true for these circular orbits. It's sort of an analogy, if you will, so that as long as that satellite is being held by gravity, it's going to have a total energy that's less than 0. When it gets to 0 or beyond, that means that the satellite has actually escaped from the gravity of the object. In this case, it would be the Earth. So it does mean something. Okay, so let's do some examples for these problems using what we know. So here, this one's pretty straightforward. It's just kind of using the expressions for potential and kinetic energy. So we're talking about an orbiter that was launched into space. It's a certain distance away from the Earth, so that's our R, and then this is how fast it's going, that's our V. So the first question is we want to find the spacecraft's kinetic energy relative to the Earth. So kinetic energy is 1/2 the mass of the satellite times v squared. Now our V is given as 1.2 times 10 to the 4 kilometers per hour. We can't put that into the expression for kinetic energy in its present form because our units will be all messed up. So let's do some unit conversion. I urge you to do this method so that you keep your conversion straight and know that your units are going to cancel out properly. So since hours is in the bottom here, we want to multiply by a fraction equal to 1 with hours on the top. 1 hour is 3,600 seconds, and so hours will cancel, and we'll be given in units per second. And then 1 kilometer on the bottom here, because kilometers on the top, is 1,000 meters. And then kilometers will cancel out. Our answer is going to be in meters per second. And so we get 3.33 times 10 to the third meters per second is our velocity that we want to use here. So kinetic energy is 1/2 times the mass of the satellite with 629 kilograms times the velocity squared in meters per second. And this turns out to be 3.49 times 10 to the 9 joules. So that's my kinetic energy. Now, I then want to find the potential energy. U is equal to minus G, mass of the satellite, mass of Earth, over R. So it's minus 6.67 times 10 to the minus 11. The satellite is 629 kilograms. The mass of the Earth is 5.97 times 10 to the 24 kilograms. And our distance, this is another one we have to be careful of. Here, R was given as 2.87 times 10 to the 6 kilometers. So we know that 1 kilometer is 1,000 meters. It means that we're just going to multiply by a factor of 10 to the third, so it's 2.87 times 10 to the 9 meters. And that's what we'll use here. And then if we multiply that out, we get the orbit is minus 8.7 times 10 to the 7 joules. If I add to get the total energy, which is the kinetic plus the potential, you might notice that my kinetic energy is larger in magnitude than the potential energy. So this is actually going to be greater than 0. And what that means is that the spacecraft is not bound to the Earth, which makes total sense. We don't want it to be bound to the Earth because it's going out into space so that it can orbit around Mars. Another idea that uses energy is the idea of escape speed. And basically, the escape speed is how fast an object has to go or leave from the surface or a location in its orbit so that it can't come back down, that like it gets so far away that by the time its speed has slowed to 0, the gravity is too weak to pull it back to the surface. So we use the total idea of the total energy is conserved. The initial energy is equal to the final energy. And then the initial energy is, of course, initial kinetic energy, initial potential, and then final. But we have to make some special assumptions. To find the expression for escape speed, we assume that it's leaving initially with the escape speed, and then, oops, sorry, that's minus. It has a potential energy, and I'm just going to use the mass of the planet over the radius of the planet. And then what we say is when it gets to its furthest point, its kinetic energy is 0, and it's so far away from the object's gravitational field that the potential energy gravitationally is also 0. And so this means that the escape velocity, if we rearrange this, is given by 2g, the mass of the planet, over the radius of the planet, and then of course we take the square root. And that's how we get that expression, in case we forget. It's not something we want to try to memorize. So if we do Mars, the escape velocity, we would use the mass of Mars and its radius. The mass of Mars is 6.242 times 10 to the 23rd kilograms. Notice it's a little bit smaller than the Earth. It also has a much smaller radius. And then we find it's 5.03 times 10 to the third. That's meters per second. We would usually just say it was 5.03 kilometers per second. Okay, so let's just look at this. The 5.03 compared to the escape velocity for the Earth, which is 11.2. Escape velocity is a term that we will often use to represent sort of relatively the strength of the gravitational field of that planet, because the stronger the field, the larger the escape velocity is going to be. If Jupiter, the escape velocity for Jupiter, we just replace the mass and the radius that we had previously for Mars by those values that correspond to Jupiter. So the mass of Jupiter is 1.9 times 10 to the 27. Notice much bigger than Earth, and also in terms of its radius as well. And we end up getting an escape velocity at 60.2 kilometers per second. And so we can sort of compare all those escape velocities. Jupiter, of course, is the largest because it has the most powerful gravitational field, while Mars is the smallest because it has the weakest gravitational field. And that's sort of how we sometimes use the idea of escape velocity when we're talking about planetary motion. Okay, so the last question that we're going to look at is a satellite put in a circular orbit 790 kilometers above the surface of the Earth. And so it's important that we understand what this means here. Here's the satellite. This is the 790 kilometers. So R should be given as the radius of the Earth plus the 790 kilometers. So we have to be careful that we understand that. So the radius of the Earth is 6.37 times 10 to the 6 meters. And then we want to add 790 and change it times 10 to the third to put it in meters. And this gives us a radius for this particular problem of 7.16 times 10 to the 6 meters. Okay, so if we're going to be dealing with a circular orbit, we're going to use the idea that the force of gravity gives us a centripetal force, centripetal acceleration. So we have g, mass of the satellite, mass of the Earth, over radius squared is equal to mass of the satellite, velocity squared over r. Notice it doesn't even matter how big the satellite is, and so we're going to solve for v squared, and it's g, mass of the Earth, over r, and then v will just be the square root of that, g, mass of the Earth, over r. 6.67 times 10 to the minus 11, mass of the Earth, 5.97 times 10 to the 24, and then the radius is this 7.16 times 10 to the 6. And we find our velocity as we calculate it is, just looking at my notes, 7.46 times 10 to the third meters per second. And so 7.46 kilometers per second, if you will. So that's how we find that. Here it says what is the period of orbit. Remember that 2 pi r is the distance it would go. The amount of time it would take would be the period, and that would be velocity. Distance over time is velocity, because it's going to move at a constant velocity when it's in a circular orbit. So rearranging this, the period will be 2 pi r over v. It's important to note that when we get our answer, it's in seconds. And so we have to change to hours because it wants the time in hours, and it turns out to be 1.68 hours. All right, so these are just a couple examples of how we would use energy ideas, force of gravity, and even centripetal acceleration to solve different problems in this chapter.